Hey everyone, this is a quick video to help you with some of this homework about Riemann sums, summation notation, and the limits that lead us into integration. So here's Con notes. I think it's pretty excellent and I would highly recommend reading through it. I'm just going to point out some highlights here before going on to some questions. I like the pictures. They're starting off with a very simple concept that we're going to sum up the area underneath this square root function from 0.5 to 3.5, so it gives you a lower bound and upper bound. You can see that the total width of that area is 3 units. So as they go through it, they sort of break it down here. They've got 4 equal subintervals, each of 3/4 of a unit, which is like non-standard, so it makes you think about what's going on. And then they talk you through how you can think of summing up each of those as being a width times a height, etc., etc. So read through that, it's pretty good. Then you start getting into the summation notation and how they deal with it. And then here is where they make an important point about, the width of each rectangle is going to be the upper bound minus that lower bound divided by how many times you're going to slice up that area into rectangles. So it makes sense. And then they've got this formula here that's out of our textbook, but they do make the good point that it's the right endpoint where you're starting at your initial lower bound, then you're adding on that first width of your rectangle. If you're using a left-hand bound, you're just going to start at that first point and then add on this afterwards. And so your summation notation will change where the lower bound will go from 0 to n minus 1. When it's like this in the right endpoint, it's going to go from 1 to n. So they've got these two forms here that make it really clear that you can spot this in the Khan Academy. They do a good job of giving you both versions, left hand where it starts at 0 and right hand where it starts at 1. That's a way of communicating that, which I like, and it's clear. So going right on here, this is just asking us what is the length of each rectangle. I believe we're being told 10 equal subdivisions, so from 2 to 7, that's a width of 5. 7 minus 2 is 5, divided by 10. This should be 0.5, and then I'll check that, and I go on to the next question. And then they're saying, what is the expression for the right endpoint of the ith rectangle? Okay, so here's where we're starting at 2, and then we're going up by 0.5 each time. So I can express that then as 2 plus, and then how wide are our rectangles? That's 0.5. So if I type in 0.5 and then that means that we're going to start with our first index number is 1, like we saw up here. We're going to start here with the right-hand Riemann sum, starting at 1, counting 2, 3, 4, 5, 6, 7, 8, 9, 10 in this example, because we have 10 slices, 2 every 1 unit up to 5. So we're going to start our very first, wait, they're saying a right endpoint? So why is the picture showing a left endpoint? What is the expression for the right endpoint of the ith rectangle? Well, the way they ask it in words with that picture, that's showing a left endpoint. Well, if I get it wrong, something's fishy with this, but it should be this. So 2 plus 5i. And we got it. So I think that picture is actually faulty. Anyway, Khan rarely makes mistake. Maybe you can figure it out better than I can. Anyway, next question. I think we're done with that. We're going to keep moving on because we've got other things to do. We want to approximate the area between these, this graph here and the x-axis using a right Riemann sum with 9 equal subdivisions. Okay, so if we're slicing this into 9 equal divisions and it's going from 1 to 7, that's a 7 minus 1 is 6, so 6 divided into 9 is going to be 2/3. 2/3. Okay, so it gets a little complicated here, but with right Riemann sum, remember, if I can go, I don't think I have the ability to write on this, but our sample point, our x sub I, our index point, is going to be our starting at 1 and going up each time by 2/3 because it was a width of 6 over 9 divisions. 2/3i. And then we're going to substitute that in right here. So it's 5/1 plus 2/3i. if I then multiply top and bottom by 3, I'll get 15 over 3 plus 2i plus 2. So I like this, that it's starting with our first slice, going up to our 9th slice. None of this is 0 to 8 part. That would be with the left Riemann sum, so we can rule out options D and B. And then why is this one wrong? Oh, they are right, because you have to remember at the end to multiply by the width. I was so focused on the first part, but remember to multiply by the width, and each of these rectangles has a width of 2/3. So this will be correct. All right? All right, so now moving on to the actual questions in the book. They're to the Khan Academy. They're very similar. So this is just more of the same. It's saying, all right, we've got this Riemann sum. We're being shown. It looks to me like it's left endpoints, okay? And we're counting through 5 of them. So with those, no, that's a right-hand endpoint. See how it goes up on the right-hand side of that? So that means it's going to start at 1 and count up to 5. And our sample point is going to start at -3 and go up by 1/5 of a unit. Okay, so it's going to be -3, and I can write on this. Yeah, so our delta x is going to be what? It's going to be the upper endpoint minus the lower endpoint. -3 minus a -2 is 1. That's pretty easy. Sliced into 5 different rectangles, so that's our delta x. That means our sample points, our x sub i's, our index points, are going to be my starting point, -3, and then I'm going to go up one of those slice widths each time. So it's going to be 1 over 5i then. And then I'm going to substitute this in for x. So this value is going to go right up there for x, and when I add 4 to it, -3 plus that 4 will give me 1 plus 1/5 I. So I'm looking for 1 plus 1/5 I, and then I'm going to multiply. I'm not going to forget this time. I'm going to multiply by the width of that rectangle, which is 1/5. Okay, so I should get sparkles, and I do. Go on to the last example here. This is similar, only slightly different. Which of the limits is equivalent to the following definite integral? So here, we are going from 0 to pi, a little bit unorthodox, but certainly with a trig function that makes sense. And so how many slices? Well, this is a limit, so it's just n slices. So again, to go to my delta x there is just going to be the width of my interval. So that's going to be pi minus 0 is just pi n divided by n. So that's my delta x. So every rectangle will have a width of pi divided by how many slices I have. And then my sample point is starting at 0 and going up by this amount. Okay, so now my x sub I, which I'm not even going to write, just out of saving time, is just going to be this with the I put on it. Okay, so now I want a limit that starts from n and goes to infinity. None of these are going from 0 to n because they're just all going to be right Riemann sums. But this is where I'm going to sub in my sample point, and that is going to be the pi over n times I. Pi over n times I plus 0, but that just drops out. So pi over n times I, and then how wide is it? The width of each rectangle is this. So which one of these is going to be? Is it this one? Sine pi over n times I. Yep, and why would it not be this one? Because they do not have the pi down here. So it is most definitely that one. And let's get the sparkles. There we go. All right, so hopefully that's pretty useful. Now if we go to the textbook just quickly, because that's part of your homework as well, you can see these early problems should be right in your wheelhouse, where they're giving us a very simple function. They're saying use the Riemann sum with n equals 6, so 6 slices, starting at 0, going up to 3, so that's going to be every half unit will be a slice, and then it says what does the Riemann sum represent, and then just draw that picture and work that out. The next one I want to highlight is maybe these in 17, because they're quite straightforward. Express this limit as a definite integral. where you're just going to say, okay, this is the function. There's your sample point. That just stands in for the variable x. There it is again being squared. So we're looking at the integral from 2 to 6. So lower bound 2, upper bound 6 of this, and then you just write dx with variables. That's all you're doing there, okay? Then when we get to problems like 22 is the one I think I did in the video in some detail, so do watch that. And then let's look at 27 briefly. Okay, so express the integral as a limit of Riemann sums, and that's from 2 up to 6, and it's x over 1 plus x to the 5th dx. Okay, so write that down. See if you could express that as an integral with a Riemann sums, a limit of Riemann sums. Okay, you don't evaluate it, you just write it. So you copy that down because I'm going to change screens. I'm going to go back to Khan. Hey everyone, here I am. I found my little blank piece of paper to write on. So for this last problem from our textbook, it's an integral from 2 to 6, and it's x over 1 plus x to the 5th, and should be dx there. That's our notation. They're saying express that as a limit of Riemann sums. So you need to look at the bounds. Okay, that's from 2 to 6. That's 4. So our step is going to be 4 divided by whatever n is. Okay, then we're going to start at 2. So my index value, my sample point here, is x sub I equals my starting point 2 plus then this jump each time. So as n goes to infinity, those get finer and finer, but that's the math. So think about what that means. If I only had 5 slices, it would be 2 plus 4/5 of our units would be the next slice. So then I'm going to write, it's going to be the limit. Oops, I need to write it down here maybe. Nope, I'm going to try to sneak it in right here. It's the limit as n goes to infinity, all right? And I'm going to just do that quickly. And then it's the summation. And if we're going to go from I equals 1 to n, and not 0 to n minus 1, then it's going to be this original function with every x replaced with this sample point, okay? And then don't forget to raise it to the 5th down there. So it'll just be, I'm not going to write it, it'll be that parentheses, 2 plus 4 over ni, and then down here it'll be 1 plus that exact same thing, 2 plus 4 over ni, and then to the 5th power, and then times the width. The width will be then this 4 over n. So that tells you the information that you need to know about how wide is your interval, and that will tell you where your, the 2 inside here, when you look at that, that 2 will tell you where you start. Okay, so having done that now, looking at this problem here, okay, I don't know why that's clicked on B. It is starting, we can see again, that's the width. That is the width 9 right there. So I'm not going to go from 1 to 9 because that only has a difference in our bounds of 8. So that would have been 8 over 9. So I know it's either this one or this one, okay? Then if I were to translate this into just the sample point, knowing that that width is n, it would be 9 over ni, and that would be then plus wherever I'm starting. Well, if I plug in 1 here, 1 for I, where I start, 1 minus 1 is 0. So I will be starting at 0, going to 9, we know that, and my initial square root will be 0. So it would be in a sense like 0 plus, that's like my x value, okay? And then as we look at this, if I'm taking the square root of that, which is like the equivalent when I have it as my initial value is 0. So this 9 here, that's a red herring because this original point here is just 9 over ni, okay? And this -1 is just adjusting for the fact that we're actually going from 0 up to 9. So I am going back